Good morning, everyone. My name is Akshat Agrawal, and I am currently pursuing MTech in Data Science from IIT Guwahati. Today, I am excited to present my project on building a hybrid e commerce recommendation system in the modern digital landscape where data is abundant, but relevant information is scarce. The core motivation behind this work is to move beyond the limitation of traditional recommendation methods like matrix factorization and tackle the complex real world issues of data sparsity and the cold start problem. To achieve this, I have conducted a comprehensive study implementing a dual architecture approach, leveraging the structural power of graph neural network combined with content aware capabilities of LightFM applied specifically to implicit feedback data from the detailed Rocket dataset. So let's begin with the problem context. The paradox of choice. Modern e-commerce platforms host millions of stock keeping units. While variety is good, it creates a massive cognitive burden. Users typically view only a tiny fraction of the catalog and suffer from the decision paralysis. They simply can't find what they need. This isn't just a user experience issue, it's a critical business problem. Effective recommendation engines are the financial backbone of the companies like Amazon and Netflix, driving on estimated 35% of the total revenue. However, a most real world data is implicit. Users rarely rate products from 1 to 5 star anymore. Instead, they click view or add items to a cart. My goal was to build a personalized curator that can infer strong user intent from the noisy implicit signal, filtering out the noise to drive conversions. So, the limitation of the traditional method. For the matrix factorization was good but fails with sparse data. Deep learning is better but computationally heavy. Historically, we have relied on methods like matrix factorization popularly popularized. While matrix factorization is effective for dense data, it has a major flaw. It suffers from the Harry Potter effect. The traditional models are great at recommending the popular items that everyone interact with, but they fail miserably the tail, the niche items that make up the majority of catalog. Further, in the dataset, I have utilized the interaction sparsity over 99% when a user item in matrix is that empty. Traditional algebraic decomposition struggles to find meaningful patterns. This results in a system that has recommends popular items to everyone, losing the value of personalization. First, to address the cold start problem where a new item has no clicks, I implemented Light FM. This model integrates This model integrates item metadata such as category ID, so even if no one has clicked a new product yet, the model knows it belongs to electronic and I can recommend it accordingly. Second, to address sparsity, I implemented graph neural networks. Standard models only see direct relationships. User A, just for example, user A bought item B and user C also bought item B, so user A and C share a latent preference. This transitive logic allows us to bridge the gap in the sparse data and make intelligent recommendations even with limited directed interactions. I utilize the retail rocket dataset which covers 4.5 months of real world behavior. The most significant engineering challenge here was the extreme class imbalance. As you can see, 96% of the data has only has simple views. Actual transactions are less than 1%. If I train a standard classifier, it would achieve 99% accuracy by simply predicting no purchase for everything, which is statically accurate but practically useless. To fix this, I engineered a weighted scheme. Views are assigned a weight of 1, cards are assigned a weight of 2, transactions are assigned a weight of 3. This converts a classification problem into a regression problem of user interest intensity. Additionally, I applied K-core filtering to remove users with a fewer than 5 interactions. It effectively filtering out bounce traffic to ensure the model learns from the meaningful sessions. Now let's look at the solution of Light FM. So, unlike standard factorization that learns embedding only for the ID, Light FM learns embedding for features. For example, it learns a vector for the category gaming mouse. This allows the model to generalize unseen items based on their attributes. A crucial detail here is the loss function. I utilized weighted approximate rank pairwise loss. Unlike MSC, which tries to predict the exact rating, WARP optimizes for the rank. It repeatedly samples the negative impact items until finds that the model incorrectly ranks higher than a positive item and then updates the weights. This ensures that the relevant items are pushed on the top of the recommendation list. Now, now for the core innovation, the graph neural network. I modeled the data as bipartite graph where one of the set of nodes represents user and other represent items. Edges interact represent interactions. I use spectral graph convolutions to perform message passing. Here is the intuition in layer 1. A node a user node aggregates features from the items they directly interacted with. In layer 2, the aggregation goes a step further. The user aggregates information from other users who interacted with those same items. This effectively mathematically encodes word of mouth or the wisdom of the crowd. It smooths the feature of the graph, allowing information from popular head nodes to propagate to the niche tail nodes, solving the coverage issue I mentioned earlier. Implementational details. So, implementing this was computationally intensive and agency metrics for 500 1.4 million users and 2035 uh, 235,000 items is massive, far too large to fit into a standard RAM. I handled this For handling this, I used PyTorch geometric for efficient sparse matrix multiplication. I ran the training on a NVIDIA Tesla T4 GPU using Google Colab Pro. Crucially, to prevent out of memory errors, I implemented sub graph sampling instead of training on the whole graph at once. The model samples small neighborhoods during each training step. This step allows the method to scale to this model allows to scale to millions of nodes without requiring a supercomputer. Now, now talking about the evaluation metrics. So, uh, I got a AUC score of 0.816 on the test set and RMSE of 1.4. So, what is the interpretation? So, the interpretation is the model ranks a relevant item higher than a irrelevant one 81% of the time. The model successfully distinguishes between low interest and high interest. So the result is hybrid plus GNN successfully captures both ranking order and interaction intensity. Based on the results, we evaluated the models on our test set of 20% of the data. For the hybrid light FM model, we achieved an AUC score of 0.816. This is a strong result for implicit data. It means that if we pick a random item, the user actually liked and the random item they don't. The model ranks the correct item higher 81.6 of the time. For the GNN, we looked at RMSE achieving a score of 1.5. Since we are we are using the weights, since we are using the weights 1.2 and 1.3, the errors of 1.5 means the model can realize distinguish between no interest and high interest, though it sometimes struggles to differentiate between a view and a card due to inherent noise in the data. So, performance by user activity. So, I wanted to go deeper than just global averages. So, I segmented the users by activity level. So here segment the users into the activity level. So this leads to the most critical insight of the project. For power users, both models perform exceptionally well with the AUC approaching zero point 0.9. The GNN shines here because the graph connectivity is dense. However, for the cold start users, the performance dropped to 0.65. The GNN struggle here because the nodes are isolated. There are no paths for message passing. This information a real world deployment strategy. We should serve new users using the light FM model. As they generate history and connect to the graph, we dynamically switch to the GNN model to maximize the accuracy. Here to make these metrics concrete, let's look at a qualitative example for our test set. The gamer profile, we had a user who viewed a PS4 console, a gaming mouse, and an HDMI cable. The model recommended Red Hat Redemption with 94% confidence. This is a fascinating because the user never explicitly searched for the game. The recommendation happened because the GNN detected a strong collaboration signal. Other users who bought consoles also bought the specific game. Simultaneously, Light FM matched the gaming category tag. This validation confirms the model is not just memorizing, it is reasoning about relationships. Future direction. In conclusion, this project demonstrates that relying on a single method is insufficient. For modern e commerce, by combining factorization with graph topology, we can effectively illuminate the long tail and provide accurate recommendation even in sparse dataset. For future work, I aim to integrate temporal dynamics. Currently, the model treats interaction as a bag of events. However, order matters. Viewing a phone then a case is different from viewing a case then a phone. Implemented sequence models like SAS, RAC, or transformers would be the next logical step to capture this intent. Thank you for the time and attention. I am now happy to take any questions. If you have, you can mail me at my Gmail ID akshat.a@iitg.ac.in.